Okay, so what we go, is it all out? You can actually pull it out. Right. That little button on the side. Okay, so what we go over today, guys, should seem familiar from Science 10. Okay, we're going over position versus time graphs and velocity versus time graphs, which you did in Science 10. Same two graphs. Not going to ask you to do anything different with them in Physics 20 than you did in Science 10. Push the button on the side.
Oh, really?
Yeah, right side, right side. Where the key is there, it doesn't actually lock. All right, so key points for today. Understand what information can be read from the graphs. Okay, so what can we read off a position time graph? What can we read off of a velocity versus time graph? Okay, what can we calculate from each one? Okay, and understand the graphs and equations from kinematics show the same information, okay, but they do it in different ways. You're going to see today that many of the formulas we use are actually derived from certain types of graphs. Okay. All right, and then lastly, okay, learn the kinematics equations are obviously derived from graphing. So they're showing it in different ways, okay, and that's what we're going to look at today. Okay, there we go. All right, so in a position versus time graph, what can I read directly off a position time graph? Exactly, the position and the time. I can see on that graph where the object is at any point in time that is on the graph. All right, so if I'm looking at this graph here, okay, that is ostensibly about a train, okay, that is moving towards a station and then away from a station, I can see where the train is at various points in time. Okay, I can see that at time 0.1 hours, it is at a sign that is, well, it says there the dot is 18 kilometers away. All right, now at that time it says it's traveling at a uniform velocity. Okay, so from this point here, okay, so from this point here to this point here, it is traveling at a constant velocity. How do I know that? Besides the fact that it's written on that graph. I think I heard somebody whisper it. It's a, what kind of line? It's a straight line. Yeah, okay? From here to here, the line is straight. Okay? Meaning that it's changing its position by the same amount every time interval. Okay? So, like for the first, well, you know, a little bit here, and then over the same amount of time. Okay, those two triangles are supposed to be identical, but I didn't draw very well. Okay, the amount it goes over and the amount it goes up are the same. Okay, it's got a constant slope there. All right, that constant slope would be the velocity of the train at that particular time. Everyone kind of follow me there? So anytime I see a line that is straight on a position versus time graph, what I'm seeing is the position changing at a constant rate. Well, according to this formula, which is on our formula sheet, okay, when the position changes at a constant rate, I am traveling at a constant velocity. Okay? Now, during this part of the graph, right here, okay, the line is curving. And the graph says that it's decelerating, which is not a term we typically use in physics, but okay, it's there. It means it's slowing down. How does that shape indicate that it is slowing down? Back here, the slope was constant. What's happening to the slope of the line here?
It's bending.
Yeah, it's bending. Is it getting flatter or steeper?
Flatter.
It's getting flatter. Okay, right? Like this is going from being very steep here to getting flatter and flatter and flatter until it gets to here, and then the line is completely flat, completely horizontal, right? If I have a horizontal line on this graph, what is the object not doing? It's not moving. Okay? A horizontal line on any graph says whatever's on the y-axis is no longer changing. Right? So if I see a horizontal line on a position time graph, it means the position isn't changing. Time is passing, but the position isn't changing. Everybody follow me there? So when I see a line getting flatter, okay, and I see a position versus time graph, I see that the rate at which position is changing is slowing. Okay? It's getting smaller, which means the object is slowing down. Everybody all right with that idea? Okay? These are the kind of interpretations that you guys are going to be expected, or actually are already expected, to be able to do. Look at a graph and say, here's what's happening. Okay? That's not memorization. I didn't memorize any of that stuff. I just looked at the graph and went, oh, it's straight. If it's straight, then whatever's on the y is changing at a constant rate. In this case, it's the position. So if the position's changing at a constant rate, it's moving at a constant velocity. I don't have to memorize that. I can analyze it from the graph. Okay? All right. Now, after this period of time where it's stopped at the station, okay, the line does this and curves upwards. Now, it's labeled as accelerating. How do I know that on that line it's going faster?
It's getting steeper.
Exactly, it's getting steeper here. Okay? In this particular part of the graph, okay, for this 0.1 seconds, it only goes this far. But in the next 0.1 seconds, it goes that far. Is that a lot further? And similarly, okay, over this next 0.1 seconds, looks like it went even further. Okay? I'm just analyzing the graph. I'm not memorizing that a curve on a position time graph means acceleration. I'm looking at that and going, it went further in the same amount of time, and then it went further again in the same amount of time. Well, the only way you go further in the same amount of time is to go faster. Okay? That's the kind of graphical analysis we expect you to be able to make. Okay? That can be easily tested in a multiple choice question on a unit exam. Okay? I give you a graph and I ask you what's going on. Okay. All right. So, is that ringing a bell a little bit from position versus time from Science 10? Okay. So, you could have graphical analysis that looks like that. You could also have mathematical graphical analysis. Calculate the slope, or what's the total displacement here, things like that. And that's what we're going to look at next. Okay, so on this particular graph, okay, I can see that it is a position versus time graph, right? I see position, or this should actually say position in meters here, okay, and I see time in seconds here. How would I mean, I can calculate the slope of the line that way, rise over run, okay? What's another way? Is there a formula I can use besides that one? Y equals mx plus b. Okay, you will be expected to use that formula in Physics 20 as well. Okay, what part of that formula stands for slope? N. Okay, N represents the slope. All right, here's why. If I solve for m, I would subtract b over here, and then I would divide by x. This and that, are they saying the same thing? Okay, so if I do this analysis, I look at this, I go, okay, slope is y minus b over x. That's true on any graph. On this graph, y minus b is the change in position. Okay, I'm taking the final position, that would be this number here, and I'm subtracting the initial position, which, sorry, would be right here. Okay, this is y, this is b. This is the y-intercept, right? This is where the line goes through the y-axis. Okay, so that's my final position, that's my initial position, because on this axis is position in meters. Okay, along this axis, obviously, is the change in time. The change in time between here and here, okay, is x, because x1 is 0. Right? Everybody okay with that? Okay. So using y equals mx plus b is typically the way we do kind of our single linear function type of calculations. We'll use it quite a bit. Okay. Can I do that analysis on any graph? Okay. On this graph, the slope represents the yeah, velocity, speed. Yeah, on this graph it represents velocity. Okay, why? Because if I go y minus b, what I'm doing is going final position minus initial position, and then I'm dividing it by x. What's on the x-axis? Time. I'm pretty sure I've seen that formula somewhere before. Okay. Guys, what often happens in Science 10 is people memorize, oh, this is how I calculate this from a position time graph. This is how I calculate this on a velocity versus time graph. And if you're a good memorizer, it gets you by. It's not always going to be like that, okay? You need to be able to analyze graphs. By the time you're done with Physics 30, you're going to have, if you're a memorizer, you're going to be memorizing 24 or more different graphs. And I don't like your chances of keeping them all straight. Okay? It's easier to learn this one skill and use it on every graph than to memorize 25 graphs. Okay? Would you agree? Okay? So here's all I did. I know this formula can apply to any graph with a linear function. Okay? One diagonal line. All I do is set it up and then look at what goes into that formula. What's on my y-axis? What's on my x-axis? When I plug it in, do I have a formula that looks like that somewhere? Okay, what does that formula solve for? Okay, one of the key points for the lesson today was that the kinematics equations are derived from graphs. Did I just derive v equals d over t from this graph? I did. Okay. I derived that on this graph, the slope of that line is the change in position over time. Okay, that's where v equals d over t comes from. Right? You can do that on any graph. Okay, and I'm going to show you that you're going to do it again on the velocity time graph. Okay, on velocity versus time graph, it's going to represent something else. Okay, but the method is the same. Okay. On this graph, okay, I would like you, come on. Okay, I would like you guys to calculate a couple of things for me using this graph. Okay, I'm going to give you a few minutes to see if you remember from Science 10 how you would do these things. I asked my Science 10s to do all 3 of these things on their physics, or all 5 of these things on their physics unit exam. Okay, so a whole bunch of you, I know you know how to do it because I've seen you do it. Okay, all right, give you a few minutes. Okay, let's look at number 1 because if you really remembered Science 10, this should have taken you about that long. Okay, what's the total displacement? 0. How do we know that? What's my initial position? What's my final position? Then I displaced myself. I ended up back where I started. Agreed? Okay. distance, scalar or vector? Scalar, which means it always gets bigger. Okay? It can never go backwards. Okay? It's always going to get bigger. So if I want to know the total distance for the whole trip, I have to figure out how far it goes in each part and then do what with all those parts? Add them together, right? Because distance is always going to get bigger. I'm just going to keep ending up further and further away distance-wise. All right, in section A, we start at 0, we go to 6. How far did we go? 6. Okay, how far did we go in part B? 0, right? The start of B, I'm at 6. The end of B, I'm still at 6, so I didn't go anywhere. In part C, I go from 6 down to -10. How far did I go? 16 meters. Okay, how far did I go in D? Stayed the same, right? Didn't go anywhere. My position was -10, and at the end of D, it was still -10, so I didn't go anywhere there. That one's still a 0. All right, in part E, I went from -10 to -4. Okay, another 6, and how far did I go in F? Another 4, right? Or from, well, over that whole section, I went from -10 to 0. Okay, so it's 10. All right, can I calculate how far I went now? To calculate each section, did I still go final position minus initial position? Right, I went 6 minus 0. I went 6 minus 6. I went -10 minus 6. Okay, I went -10 minus -4. I went -4 minus 0. I still used final position minus initial position, but I recognized that I don't have any positives or negatives because I'm solving for a scalar quantity. Okay, so when I add all those up, what do we got there? 28, 32. Okay. So the total distance traveled is 32 meters. All right, if I want to calculate the average speed, have I just done most of the work for that? Okay. How do I calculate average speed? Distance divided by time. Okay, so average speed, total distance divided by total time, 32 divided by, we said 18, okay, where that comes to. All right, so 1.8 effectively meters per second. Okay. I'll give you a little bit more time on 4 and 5. All right, so looking at this here, this graph, okay, we have a linear position versus time graph. All right, before we do any calculating, what is this object doing? It is traveling at a constant velocity in a positive direction. Okay, what's the velocity of this object?
4 meters per second.
Close. Slightly less than 4. 3.85. Okay, I know what you did. You went, okay, 60 divided by 15, right? You got 4?
No.
Oh.
Oh, I can see. Oh, I didn't see.
You were close though.
Yeah.
Whatever you did, it was close.
Well, no, I just looked at like the dot there and I thought.
Oh, okay. You looked at one dot, right?
Yeah, and I'm like, okay, 520.
Right.
I thought it was
went
on
4.
the
Yeah,
thing.
but it's just a little bit below 20, right?
Yeah.
Okay. So where did you get the 3.85? Okay. If I write this formula out, what this formula is really saying is this. Okay, so it's like y equals m times x plus b. So the 3.85 is the m, the negative 0.801 is b. That's supposed to point at the b. Okay. Why is the slope the velocity on this graph? Okay, let's go back to something I did on another graph earlier. If I want to calculate the slope, n, I manipulate that formula and it looks like this. Y minus b over x. Okay, what's on the y-axis? Position. If I have one position minus another position, am I doing that? What does final position minus initial position equal? Displacement. What's on the x-axis? What does d over t calculate? Velocity. Okay? I don't have to memorize that the slope of a line on a position time graph is equal to the velocity of the object. I can figure it out. If I can figure that out, I can figure out what it is on a velocity time graph. And energy versus work function graph and whatever other crazy things you're going to get in physics 30. Okay? All right. I want you guys using y equals mx plus b, in particular the equation at the top of the graph, see what we remember from math 10. Okay? Calculate for me the position after 1 minute or 60 seconds. Okay? And calculate for me how long it will take to reach a position of 150 meters. Okay? It's just y equals mx plus b. You did in both math 10 and you did in science 10 as well. Let's see what you remember from that. All right, if I'm looking at this graph, okay, if I want to solve for position, what part of the equation am I solving for? Y. Okay, because position is on the y-axis. Okay, so I need to solve for whatever y is when x is 1 minute. How do I know the 1 minute is the x value?
It's time.
Yeah, it's time. Time is on the x-axis. Okay, so if a question gives me a value that corresponds to one axis or another, that's where I put it in. Time is on the x-axis, so I substitute in 60 seconds for x. Okay, and then I solve for y. Right, so I'm just going to go y equals, okay, m 3.85, okay, 3.85 meters per second times 60 seconds plus negative 8.801. So if I take my displacement and add my initial position, that should give me my final position. Agreed? Okay, that's what I'm doing here. Velocity, time, initial position. Okay, so the position after 1 minute will be 230 meters. Actually, it'd be 2.3 times 10 to the 2, but we'll just say 230 for now. Okay, everyone follow how I figured that out? Okay, the biggest thing for using the graphing equation is to understand what's on my graph.
Where'd the 8.01 come from?
That's the y-intercept. So the line
Oh,
actually goes a little bit below the x-axis here, so where it crosses the y-axis is actually a negative.
I see that.
Ever so slightly. Okay, what am I looking for in number 2? Y or x? I'm looking for x. How long? That's time. I'm looking for an x value, and I know that for, well, because of that, but also because they tell me a position, which is a y value. Okay, so I'm going to take my y equals mx plus b, and I'm going to solve for x. So I'm going to subtract b over to the other side, then I'm going to divide both sides by m, okay, and that will leave me with x. So 150, that's the y value they gave me, okay, minus negative 0.801, that was my y-intercept, divided by the velocity. So here's displacement divided by v. D over v equals t, okay, and that will be 150 plus 0.801, okay, divided by 3.85. All right, that's going to take 39 seconds. Okay, is that ringing a bell from Science 10? And Math 10? Okay. I can't remember if that was the exact graph I used in my Science 10 unit exam. It looked something like that. I asked pretty much the same thing. All right, questions on what we did there? Okay. All right, on this graph here, which object is going faster, blue or red?
Red.
How do you know?
Tires.
Steeper, yeah. Okay. Right? If on a position versus time graph, the steepness of the line kind of indicates how quickly you're changing your position. Would you agree? Right? So the steepness of the line, which equals the velocity, if it's steeper, it's faster. Okay. I would like for you guys to calculate for me two things. Okay, question number one, how long for each object to reach a position at 10 meters? Okay, and what the position of each will be after 12 seconds. Okay, let's have a look at number one. So if I'm looking for how long on a position versus time graph, what am I solving for, y or x? X. Time is on the x-axis. If I'm being asked to solve for a time, then I'm solving for x. Okay, they gave me y. They said y equals 10. Okay, I already know for each one of these what b equals. I already know for each one of these what m equals. Okay, so the only things I don't know are y and x, and they gave me y for the first one. Okay, so I simply go, all right, x equals y minus b, okay, divided by m. All right, so for the red line, okay, that's going to be 10 meters minus 0.115 divided by 0.38. Okay, and for the blue line, okay, that's going to be 10 minus 0.195 divided by 0.26. Okay, let's do those calculations. Okay, 10 minus 0.115 divided by 0.38. All right, so it'll take 26 seconds for the red one. Okay, and for the blue one, 10 minus 0.195 divided by 0.26. All right, that's going to take 38 seconds. That makes sense. The blue line is slower. It should take longer. All right, I'm going to give you guys a couple more minutes on number two, okay, and then we'll go over that one. Okay, so for number two, okay, we're looking for just the position. Position's on the y-axis. So for question number two, we are simply looking for y. So we just plug in numbers. Y equals mx plus b. Okay, so for our red one, okay, that is going to be, we were looking for 12 seconds here. So we're going to take, for the red one, 0.38 times 12 seconds plus 0.115. Okay. 38 times 12 plus 0.115 All right, so 4.675, so we'll just say 4.7 meters, and that would be positive, okay, because we're solving for a position. All right, and then for the blue one, okay, we'll take our 0.26 times 12 plus 0.195. Oh, that's 12 plus 0.195. Okay. So we're looking at 3.315 for that one, which makes sense. It shouldn't be as far. Sorry, we had 3.3. Positive 3.3 meters. Okay, is that ringing a bell? Feel at least somewhat familiar to use y equals mx plus b? All right. I want you to answer those three questions for each of the carts on that graph. Why will it take next to no time at all to do that? Because m's velocity calculation's already done for me. Okay? The slope of each one of these lines is how fast that object is going. And I know the slopes. For the blue one, it's 1.38 meters per second. For the red one, it's 2.01 meters per second. And for the yellow one, 3.39 meters per second, which fits the yellow line is the steepest of the three lines. Okay, therefore that is the fastest of the three carts. All right, now just for justification on that, remember that if I solve for m on a position versus time graph, doing this, what I'm really doing is taking the final position, that would be right up here, minus the initial position, that would be my y-intercept down here, and dividing by time. That is how we calculate velocity. That is why the slope of the line equals velocity on this graph. All right, for each one of these, the position of the cart after 12 seconds. So y equals m times x plus b. This would be the final position. They gave me 12 seconds, so they gave me x. I already know m and b for all three of those. Okay, so for the blue one, okay, we're looking at 1.38 times 12 plus 0.00952. Okay, so the final position of the blue cart will be 16.6 meters. Okay, actually, there's only two significant digits there. 17 meters, okay, would be the final position positive of the blue cart. Okay, for the red cart, 2.01 times 12 plus negative 0.0524. All right, final position of the red cart is going to be 24 meters, positive 24 meters. And for the yellow cart, 3.39 times 12 plus 0.0381, 41 meters positive for the yellow cart. Okay, questions on number 2? All right. Question number 3 is asking for how long it would take each one. Okay, so that's going to be that x equals y minus b divided by m. Okay, if I'm solving for x. So since they're all 50 meters, it's going to be 50 minus 0.00952, okay, divided by 1.38. Okay, so it will take the blue cart 36 seconds to reach a position of 50 meters. For the second cart, it will be 50 minus negative 0.0524. Okay, whoop. 50, oh, gotta cut 2 decimals in there. 50 minus negative 0.0524. That's better, it'll like that mark. Okay, and then divide that by 2.01. All right, we're looking at 25 seconds for that one, and for the last one, 50 minus 0.0381. okay, divided by 3.39. Okay, and logically, that one takes the least amount of time because the yellow line represented the fastest cart, so that would take 15 seconds. All right, everybody with me there? Okay. I could very easily ask you something like that on next week's quiz. Not this week's quiz, because this week's quiz is just on vectors. Okay. All right, so on this one here, you got an irregular position versus time graph. So I would like you to do the calculations requested there. The answers are there in bold, so you can check them as you go. Okay, let's have a look at this one here. So if I want to know the velocity during each one of these parts, for part A, okay, velocity is displacement divided by time. Right, I'm going to have 25 kilometers minus 0 kilometers over 1 hour. So positive 25 kilometers per hour would be my velocity during part A. Okay, pretty simply. For part B, same calculation, okay, except this time I'm going to go final position, 33, minus initial position, 25, and that took 1 and what looks to be a quarter hours. All right, so 33 minus 25 divided by 1.25. All right, should give me 6.4, and in a positive direction, kilometers per hour. And then for the last one, okay, same calculation again, but this time it's going to be 27 minus 33. Final position minus initial position. I believe that takes another hour and a quarter. Okay, so we'll have -6 divided by 1.25. Okay, negative 4.8 kilometers per hour. Why is it negative? Right, we're going in a negative direction, right? We went from 33 to 27. We're backtracking now. Okay, and then over the total, okay, well, to get the average velocity over the whole trip, that would be total displacement divided by total time. Okay, the total displacement is positive 27 kilometers divided by 3.5 hours, okay, which should give us positive 7.7 kilometers per hour. Okay, everybody all right with that? Okay, we'll call it a day there. You guys worked pretty well today. Okay, tomorrow's quiz, vectors, vectors, and more vectors. Okay, be ready for it. Okay, also remember, math activities are due tomorrow beginning of class, so make sure you bring yours along.